So before starting this video, I'd love to thank Reliable for sponsoring this entire tree series. So do you wish to work with companies like Cred, Upgrad, Urban Company, Razorpay, but you are not able to apply because of your lack of experience and of lack of opportunities? So here's a solution to this problem. Reliable by Unacademy is a hiring platform that helps freshers and experienced people to get jobs in India's top companies. All you need is skills. So what you need to do is you just need to give the Reliable test that is completely based on your skills. Depending on your performance, your interview will be scheduled and you will be hired from the Reliable platform. And the best thing about this is it's absolutely free. So what are you waiting for? Please make sure you check out the links in the description. Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem, flatten a binary tree to a linked list. Now you might be thinking, oh, this is an easy problem. What is tough in it? It is tough. It is tough. Now let me tell you how do you need to flatten it, and then I'll tell you why it is tough. So basically, what you need to do is you need to make this a linked list into something like this. Okay, like a linked list like this. So if you write down the pre-order of this, it's going to be 1, 2, 3, and then a 4, then a 5, then a 6, then a 7. So whatever is the pre-order of this binary tree, that is how you have to represent a linked list. Now you'll be like, Trevor, that is easy, isn't it? Why? Because Trevor, what we will do is we will take 1, we will create a node, we'll insert 1. Then we'll create another node, insert 2 and point 1 to that. Then we'll again create another node and insert 3. This is where you will go wrong. You don't have to create a new linked list. No, you don't have to create a new linked list. You have to rearrange these nodes. I repeat, you have to rearrange these nodes such that 1's right should be pointing to 2, 2's right should be pointing to 3, 3's right should be pointing to 4, 4 right should be pointing to 5, 5's right should be pointing to 6, 6 right should be pointing to 7. That is what you have to do in order to flatten a binary tree to a linked list. So definitely you cannot create an external. You have to rearrange the tree. Okay. So how to solve this problem? So what will be the recursive solution? So if I just think of this, first, if I just break down this link and I attach it to 6, right, that will make it 7. Okay. Now what if I just break this link and I break this link and I take this entire tree and I just convert this tree into something like 2, 3, 4, and then I have 1's right attached to 2 and 4's right attached to 5. I think this is how I can actually do. So in short, can I say, like if I just think it in a very distant manner, can I say if I can do a traversal so that I can reach 6 at first, which will ideally mean that I have to traverse first right, and after that I can do the other job, because first I'll go in, I'll do the job for 7, then I'll come back and do the job for 4, and then the job for 2, and so on. So ideally it should be left and then right, first right, then left, then root. Like that should be the logical solution, because first I'll arrange 7, then I'll arrange these guys, then I'll make then I'll work with 1. So it's kind of a right, then a left, then I'll work with the upper guys. Perfect. So right, left, root. It's not a post order, it's not an in order, it's not a pre-order. It's kind of a reverse post order. You can call it reverse post order if you want to. So this is what my thought process will be. I'll try to do a reverse post order kind of a thing and try to first attach 7 to 6, and then probably 4 to 5, and so on. That is what my thinking will be. Okay, so let's see how I can do that. Okay, so this is the piece of recursive code that's gonna work for the kind of approach that I was discussing. And I'll be like, how did you come up with this? It's a very easy one. I'll explain you about the intuition while explaining the code, because if I explain the intuition normally, you'll not be able to connect it. So once you understand the code flow, then understanding the intuition won't be a big deal. Okay, so what I'll do is I'll initially have previous equal to null. Okay, I'll start with the root. So that's where I start off with, and then I go to the right. So that's where I go right. Then I again come back and I again go to the right. Perfect. Then I again come back, go to the right, and I find a null, so I'll return. So when I return, the right is done. So I'll go to node dot left. So this is where I go, node dot left. Now this one has no right, no left. So I can say when I'm at 7, the right is null, the left is null. So nodes right should be pointing to previous. So nodes right is pointing to null, and nodes left should also be pointing to null. Why is nodes right pointing to null? Because previous is initialized as null. Perfect. So since I did not need to do any modification, I made it as like this null. Okay. So once they have been pointed to null, it's time that previous should be updated with 7. So please update previous with 7. Now, what's the next step that you will do? 6 did its right? 6 did its left. Now 6 will perform these. See, 6 does what? 6 says, my right will be connected to previous. That is 7. That is 7. So 6 right is connected to this node itself. And nodes left is now null. So it says it will be null now. So if I just erase it, this is nothing but null. Perfect. After that, I'm saying previous is 6. So I updated previous to 6. So understand what I did. Since I was doing a traversal of right and left, the moment 7 was completed, I stored 7 in previous. And the moment I came back to 6, right and left was completed for 6. So I took those previous guys and attached it to 6 ka right. Simple as that. And now the previous is 6. So this time 5, I'll come back to 5. 5's right is over, left is no one. So 5's right points to previous, that is to 6, and this is to null. This will point to null. Simple. Again, come back. Once right is over, remember when you come back, previous will be updated to 5, okay? Because 5 points to 6, points to null, and then previous is assigned. Perfect. Now you come back to here. Now when you go to the left, you are at 2. So right is done, left is still waiting. 2's, you'll go to the right. This guy doesn't have a right, doesn't have a left. So no more going into the flatten. So this guy will now say, my right will be previous. So this is the last guy that you completed for. I hope you're getting the intuition. This is the last guy for which you completed the entire post order. So what you'll do is you'll say, okay, why don't you go and attach it? So nodes right went in and attached to 5. That is what I was wanting. And I'm saying nodes left will be null. That is okay. Now I'm saying 4. This is the last guy whose entire stuff is done. So previous will be 4. Perfect. Comes back. 2's right is done. 2 goes to the left. 3 right, no left. So again 3's right will be pointing to 4 and no left. So the previous will be updated to 3. Perfect. So now comes back to 2. 2 says, hey, I have done right, I have done left. So 2 will say, okay, it's my time. My right should point to previous. That's 3. So it will point to 3 now. And its left should point to null. So 3's, if you remember, 3's right was pointing to 4. That is over. So that is what I'll do. Perfect. So I can say 2's right is pointing to 3 and 2's left is null. So now I've completed for 2. So the previous will be 2. Perfect. Now you come to 1. 1 says my right is over, my left is over. So 1 has to now do its job. 1 says my right should be pointing to the previous. That's 2. So 1's right now points to ultimately 2. Like that's the right node. That's the right node that's pointing to 2. And its left points to null. So ultimately if you rewrite this, now this is over. The next time the previous will be 1 and it's over. Ultimately if you rewrite this, this is equivalent to saying 1's right points to 2, 2 points to 3, 3 points to 4, 4 points to 5, then to 6, and then to 7 and so on. Correct? So what I did was very simple. The guys whose post order was completed, I stored in previous. And whenever I went to that, I just attached it. I just attached it to that. That's it. That is what I did using these couple of lines. I attached it to the previous guy whose reverse post order was completed, and I made sure there was no left out. 2 lines, and since right and left calls are over for node, I said this guy is the new guy whose reverse post order is completed. That's it. That's as simple as that. What's the time complexity? The time complexity stands out to be big O of n, and the space complexity also stands out to be big O of n, assuming the worst height is big O of n. That's about the recursive solution. So the second solution that I'll be discussing will be an iterative solution that uses a stack. Now you don't need to tell this in the interview, just know this. And again, I've written the code. I'll be telling you the intuition while explaining the code so that it gets more clear. It's basically an extension of the recursion, nothing else. So initially you take a stack, you have the root node into that. Okay. Now stack is a last in first out data structure. Remember that it's a last in first out data structure. So initially you take a stack and it will have one into that. Okay. So first time come in and cur will say st.top. So and pop. So cur will be 1. Next, does cur have a right? Yes, that's 5. Does cur have a left? Yes, that's 2. Insert that. Right after that, cur is 1, right? So over here what we'll do is we'll say once right should be st.top. So once right should be 2. So I'm directly saying, hey 1, your right should indeed be 2. That is what I'm saying. Hey 1, your right should be indeed be 2. So what I'll do is I'll just use the yellow colors to mark the right links. Okay. After that I'm saying, hey, your left is null. So I'll use the red colors to mark null. So your left is null. Perfect. Right after that, I've done this. So I come back again. And cur will be like, take 2. Okay. So cur will take 2. So I've taken 2, right? Now the moment I have 2, I again do the same thing. Take the right, take the left, and put it into the stack. Taken? Perfect. This time, I'll say 2, your right should be 3. So I'll take the top and I'll link it. So 2, your right should be 3. And I'll say 2, your left should be null. So that's what we are doing over here and over here. So once you've done this, next you will take the cur to be the next guy. That's 3. So I've taken it 3. Now you're saying 3, do you have a left? No. Do you have a right? No. So we don't have anyone. So ultimately we don't have anyone. So this time we do not push anything, but we see stack is not empty and stack is having 4. So this time we are saying 3 is right should point to 4. Again, I'm using yellow pointers. 3 is right should point to 4. And 3 is left should point to null. Red pointers for that. Done with this. Next I come again and I say 4. So the moment I have 4, I can see there is no left, there is no right, so nothing to be pushed into the stack. This time 4 says, 4 has been taken out. This time 4 says, who's the top? That's 5. 4 says, okay, connect my right to that and connect my left to null. Again, pretty straightforward. So you see 1's right getting connected to 2, 2's right getting connected to 3, and 3's right getting connected to 4, 4's right getting connected to 5. Okay, by the way, just make sure these links will not be there because you have reassigned these links. So these links will not be there. Perfect. So once you've done for 4, it's time that you take out 5. So next time it's 5. 5 says, I have a right, that's 6. But I don't have a left. Okay. Next, 5's right points to 6. Okay. And 5's left, that's null. Nice. Next time you again come back. And this time 5 will be changed to 6. 6 will say, I don't have a right, but I have a left, that's 7. And I put it. This time 6 says, my right will be 7. And my left will be null. Perfect. Next time when you come across, you have 7. So cur becomes 7. 7 says, I don't have a left, I don't have a right, so nothing to insert. And the stack is indeed empty. So cur right will be not pointing anyone. And cur left will be null. And I can say my stack is empty and I have ended my iteration. Once my iteration has ended, can I say, like, if I just join the yellow dots, it's going to be 1, 2, like yellow are the right dots, right? 3, then a 4, then a 5, then a 6, and then a 7. Indeed. And that's how you can flatten a binary tree to a linked list. Very straightforward. Insert right, insert left, and then just make sure you connect them, right? Again, it's very intuitive because you're inserting right and you're inserting left. Like if you just understand the intuition, it's 2 and it's like, just assume this smaller binary tree. So what you're doing is you're inserting 3, you're inserting 2. And right after that, you're saying, hey, let's do one thing. Let's connect this one to whichever is at the top. Like connect this one's right to whichever is at the top. So since you're inserting left at the second time, so one's right will automatically get connected to 2. right? And after that, 2 will automatically get connected to 3. That's why the intuition is of entering right first, then fall left, so that whenever you have the right attached, you'll automatically get it attached to the next guy. That's the simple intuition behind inserting right first and then the left. Time complexity again stands out to be big O of n, space complexity big O of n. So we haven't significantly improved anything except ignoring recursion. So in the method tree, we will be using a big O of 1 space. Now, if you haven't seen my Morris traversal, I'll recommend that you should definitely watch it, and like you can watch it afterwards also. But like if you have watched it previously, then it will be a very big plus. Okay, so let me explain what will be my thought process. Now, since this binary tree has to be converted into a linked list, and essentially it's a pre-order, correct? So logically, this 4 should always connect to this 5, right? That's the logic. This 4 should always connect to the right, the 5. Why does this 4 has to connect to 5? Again, a logical answer will be, since it's pre-order, this is the left subtree, this is the right subtree. So first we will have this, then we will have the entire left subtree, and then the last guy of the left subtree, that's what is the pre-order? That's basically root left right, root left right. So first you'll have root, that's 1, then the left guy, so again root left right, so root left right, and then again 5, and so on. That is what you will ultimately have. So I can say that, what if I can actually do a connection like this, and then I can connect this once right to 2. Like if I just do a connection like this, I think my job should be done, right? So that is what I'll try to do. On the left subtree, yes, on the left subtree, I'll try to figure out which is the rightmost, like which is the last guy of the pre-order, and whichever is the last guy of the pre-order, I'll try to connect it to the right of this guy, because that is essentially what we have to do, correct? So we will be writing the code keeping this in mind. So let's write that. So this is how the code will look like. Again, doing a dry run will make things further clear. So initially, I have a current which is 1, which is standing at the root of the tree. So ideally, I have to connect this 4 to 5, right? So what I'll do is, I will first see if cur has a left, because if there is a left, then only it will get connected between 1 and 5, right? If there is a left only. So if it is having null, not having null, then I'll take a previous, okay. So let's take a previous which is saying I'm 2. Okay, so I've taken a previous which is 2. What I'm saying is, go on till previous right is not null. So previous will say, okay, I can go on 4, but I cannot go beyond 4 because 4's right is null. So I'll go till 4. Perfect. Now I'm saying 4's right. Why don't you go to cur's right? Cur is 1. 4's right, that's this. Why don't you go to cur's right? Perfect. Next I'm saying cur's right should be cur's left. So I'm saying this guy. So 1's right is pointing to 2, and I've made sure that this happens. The next thing that I just need to do is I have to make sure 3 comes in between them. So I've done the first thing. Perfect. Next I'm saying cur, why don't you move to cur right? So cur's right is 2. So I moved it. Perfect. Next, let's come back again. Does 2 have a left? Indeed it has. So previous will be this time 3. And I'll go on to right if there is any. So that doesn't exist any right. So this while loop will not be executed. I'm saying previous right, previous is 3, its right should point to cur's right. So it's point to here. Again, super simple. And I'm saying cur's right, this guy's right, should point to 2. Perfect. Next I'm saying cur, why don't you move right? So cur now will move to 3. Perfect. Again you come back. Cur's left. Does 3 have a left? No, it doesn't have. So this time cur will move to again to cur right without actually performing these steps. So cur this time moves to cur's right. That's 4. Does 4 have a left? No. So cur will again move to right. That's 5. Does 5 have a left? No. So cur will again move to 6. Next, does cur have a left? Yes. So this time if it has a left, cur will be 6. Now again we'll do the same thing. So the next time you come across to 6, and the previous will be 7, right? Because it has a left, so it has a 7. So while will not be executed. So previous right should be pointing to null. Okay, and curse right, that is curse this right should be pointing to curse left itself. So this is the new node that will be created. Curse right will be pointing to 7 itself. Perfect. Next, this time cur will say I'll move to right. So this time cur will say I'll move to right. 6 will move to right, that is 7. Does 7 have a left? No. So 7 will say I'll again move to right. 7 this time moves to null. The moment cur reaches null, I can say it's over. And if you just see the yellow linings, 1 goes to 2, then to 3, then to 4, then to 5, then to 6, then to 7. Joint everyone. Again, the intuition is very simple. On the left subtree, whichever is the last guy which will be performed on pre-order, I just took that and connected to the right of the current node. That is what the simple intuition is. I repeat, on the left subtree, whichever is the last node of pre-order, I connected it to the right of the node, right of the root. That's it. That is what I needed to do. And I just kept on doing that for every tree. And ultimately, I could easily traverse and change the pointers in big of n time and big of 1 space. That's very important. Big of 1 space is what I took. So that is how we will do this. So I hope you have understood the entire explanation as well as the code. Just in case you did, please make sure you like this video because it took a lot of efforts to make this entire tree series. Also, if you wish, you can definitely drop in a comment that will keep motivating me to make such further series. Also, if you're new to this channel, please do consider subscribing because I'm going to bring in such more series in the upcoming future as well. With this, let's wrap up this video. Let's meet in the next lecture. Bye-bye. Take care.